Welcome, curious minds, to the deep dive. Today, we're embarking on an exploration that, well, it sounds like something straight out of the distant future, yet is actually unfolding right now. Can artificial intelligence, something we created, truly begin to grasp the incredible vastness and complexity of our universe? It's a question that captivates both seasoned astrophysicists and really anyone who's ever looked up at the night sky and wondered. And it's right at the very heart of our deep dive today. We're diving into the absolute cutting edge of AI research. Specifically, we're focusing on how large language models, the tech behind systems like GPT, are being deployed and, frankly, put to the ultimate test in the sprawling, data-rich field of astrophysics. Our mission for this deep dive is to unpack some recent, really groundbreaking research. We're not just looking at what AI can do, in terms of crunching numbers and classifying cosmic phenomena, but maybe more importantly, what its surprising performance might tell us about what understanding truly means, both for us humans and for these rapidly evolving machines. So how are we going to navigate this cosmic question?
Well, we'll kick things off by examining the practical, tangible ways AI is already making some genuinely surprising discoveries out there in the cosmos. Then, from there, we'll pivot. We'll look at the more profound philosophical implications of AI's apparent understanding. We'll be delving into concepts like intuition and causality, and exploring how AI might develop these abilities in ways we can barely even imagine right now. And finally, we'll pull back the curtain a bit on the advanced AI technologies that are powering these breakthroughs. And then, we'll cast our gaze towards what the future might hold as AI continues its remarkable evolution in its quest to decipher the cosmos. By the end of this deep dive, our goal is for you to have a clear, concise, and I think incredibly fascinating shortcut to being truly well-informed. You'll get the surprising facts, the mind-bending insights emerging right at the intersection of AI and the fundamental fabric of reality. You'll gain multiple perspectives, probably encounter more than a few aha moments, hopefully all without feeling overwhelmed by the sheer volume of information out there. So, prepare for liftoff.
Okay, let's really unpack this. Many of us have encountered large language models like GPT, right? We've seen them generate text, summarize articles, maybe answer questions. But what happens when you point these digital brains directly at the stars? At the raw, sometimes messy, yet highly structured data of the universe itself? Our core source material for this segment, this paper title, Can AI Understand Our Universe? Test of Fine-Tuning GPT by Astrophysical Data, gives us some really remarkable initial answers.
That's a great place to start. The fundamental concept here is something called fine-tuning. Specifically, fine-tuning a large language model for a highly specialized domain like scientific data and astrophysics. So imagine you take a general-purpose genius model, something like GPT, which has already learned an immense amount. It's processed a colossal array of human language and knowledge from across the internet. It's already incredibly versatile, right? It understands context, generates coherent text. But then you give it this highly specialized, intensely focused education. You use a very specific data set, in this case astronomical observations. And this process, it typically involves two key stages. First, there's the initial pre-training. That's where the model learns fundamental language skills, like predicting the next word in a sentence from a massive, diverse data set. This builds its foundational understanding of grammar, facts, even some reasoning. After that comes the fine-tuning phase, and this is where a much smaller, highly specific data set comes in. Often there's human supervision involved here too. It's used to teach the model how to perform very particular tasks within that new domain. This custom tailoring, it allows the model to deeply specialize. It effectively transforms its general intelligence into domain-specific mastery. It becomes sort of expert in a new field like astrophysics.
Right, okay. So it's like taking a generalist and putting them through a very specific PhD program focused only on cosmic data.
Exactly. That's a great analogy. And once these models are fine-tuned in this way, the researchers wanted to see what they could actually do.
So what were some of the first, most striking breakthroughs? What did they actually put GPT to the test on to see if it could perform in this, very different realm of astrophysics?
Right. They didn't just give it a pop quiz on astronomy facts. They put it through its paces on several really challenging, fundamental astrophysical tasks. Let's begin with the classification of celestial objects, specifically distinguishing between things like quasars, galaxies, stars, and a specific type of quasar called a broad absorption line, or BAL, quasar. This is a really foundational task in astronomy. You need to know what you're looking at.
And the context for this is crucial, isn't it?
Yeah.
We're talking about data from something called the Sloan Digital Sky Survey, or SDSS. Can you tell us a bit about that?
Absolutely. The SDSS is, well, it's truly monumental. It's its ongoing global effort to map the universe. Think of it like humanity's most ambitious cosmic census. It collects just immense amounts of data on everything from relatively nearby stars out to incredibly distant quasars. It's an absolute treasure trove of what you might call cosmic fingerprints. It provides the raw material for these kinds of AI analyses. So for this particular experiment, the researchers used spectral data from SDSS data release 16, or DR16. They carefully extracted 2,000 samples, 500 from each of those 4 classes: quasars, galaxies, stars, and BAL quasars, ensuring a balanced set. Now, this spectral data can be really high resolution, very complex. To make it manageable for the AI, particularly for a language model which thinks in terms of tokens, they did something quite clever. They condensed each spectrum down to just 100 key equidistant data points, and they normalized the values. So a complex spectrum might end up looking like a sequence of numbers, say 178, 351, 396, and so on. This optimization was crucial for efficient processing.
Okay, so they simplified the data representation to fit the AI model better. And what were the results? How well did it do at telling these cosmic objects apart?
The results were actually quite compelling. After fine-tuning the GPT 3.5 turbo model, and get this, for just 2 epochs, basically 2 passes through the training data, which was 1,800 samples, it achieved an impressive overall accuracy of 82% on the test data it hadn't seen before. Breaking that down a bit, stars were classified with 88% accuracy, galaxies at 82%, quasars at 80%, and BLL quasars at 78%. Now, there was a slight tendency. The model sometimes confused quasars with BLs, which are related, and sometimes galaxies with stars. But its ability to distinguish between, say, a quasar and a BL quasar, or between a galaxy and a star, was remarkably strong overall.
And what strikes me here is the efficiency. 82% accuracy is good, but achieving it with such limited fine-tuning data, you said less than 5% of the total available spectra.
That's right.
And using that significantly reduced sampling rate, just 100 points, instead of the full high-resolution spectrum, it really implies there's this vast untapped potential for even greater accuracy if the AI were trained on more comprehensive data sets, doesn't it? It speaks volumes about its ability to learn patterns even from relatively sparse data.
Absolutely. It suggests the underlying patterns are strong enough for the model to pick up on, even with this limited exposure.
Okay, so classification was one test. What was next? They also had to tackle inferring the redshift of quasars, you mentioned.
Yes, that was the second major task.
Why is determining the redshift of quasars so fundamentally important? What did that tell us about the universe?
Oh, quasars.
They're incredibly important probes. They're powered by material falling onto supermassive black holes at the centers of distant galaxies, making them extremely luminous, visible across vast cosmic distances. Redshift, essentially, is a measure of how much their light has been stretched by the expansion of the universe as it traveled to us. Determining it precisely helps astronomers refine our measurements of key cosmological parameters, really fundamental stuff. This includes things like pinning down the universe's expansion rate more accurately, understanding the properties of dark energy, that mysterious force accelerating the expansion. These are central questions in modern cosmology. But beyond that, quasar spectra act like cosmic probes. Their light passes through gas clouds between us and them, so analyzing the spectra gives us invaluable insights into the interstellar and intergalactic medium, the composition, density, temperature of gas across vast cosmic distances. And furthermore, high redshift quasars, the really distant ones, offer an almost unparalleled glimpse into the very early universe. We're talking about the first billion years after the Big Bang. They let astronomers investigate pivotal moments like the epoch of reionization, when the first stars and quasars ionized the neutral hydrogen that filled the early universe.
So incredibly valuable objects for understanding cosmic history. How did the AI do at figuring out their redshift?
For this experiment, they used about 4,000 quasar spectra from the SDSS, specifically focusing on quasars with redshifts ranging from 0 up to 1. They fine-tuned the model using 3,200 of these as training samples. And the results here were also quite impressive. The fine-tuned GPT model achieved a median relative accuracy of 90.66% in predicting the quasar redshift. This was significant because it demonstrated GPT's capability not just for classification, like telling objects apart, but also for regression tasks, predicting a continuous numerical value, like redshift, based on the spectral data.
The 90% accuracy seems pretty good for predicting a specific number like that.
It is, especially given the approach. But it's important, as the researchers note, to consider some nuances for achieving even higher precision in the future. The current streamlined sampling, that 100 data point representation, while efficient for the LLM, actually omits many of the specific emission lines astronomers traditionally use for direct redshift calculations based on shifting spectral features.
Ah, okay, so the simplification might be losing some key details for that specific task.
Potentially, yes. So augmenting the sampling rate, using more data points per spectrum, and increasing the overall sample size would undoubtedly help refine these redshift estimates further. Also, a specific challenge is with very high redshift quasars, say those with redshift Z greater than 6. These are extremely rare in observational data sets because they're so far away and existed so early in the universe. This means that simply relying on observed data might not be enough. Integrating simulated data, creating artificial high redshift quasar spectra would likely be essential for comprehensive training to accurately predict redshifts in those extreme early universe cases. That would really push the AI's understanding into truly uncharted cosmic territory.
Got it. So good results, but room for improvement by feeding it more detailed or even simulated data for the rarer cases. Okay, what about gamma ray bursts, GRBs? These are the most powerful explosions we know of, right?
That's right. Cosmic fireworks on an unimaginable scale.
And traditionally, astronomers classify them as either short or long, based mainly on how long they last. There's this parameter called T90, and usually a threshold around 2 seconds is used.
Correct. T90 measures the time interval during which 90% of the burst's total gamma ray fluence is detected. And yes, the historical dividing line has often been placed around 2 seconds. Bursts shorter than that are typically classified as short, longer ones as long.
But I recall reading that this method isn't perfect. There's a known challenge because the duration distributions for short and long bursts actually overlap quite a bit near that 2-second mark.
Exactly. It's not a perfectly clean separation. Some bursts near the threshold can be tricky to classify based on duration alone, leading to potential misclassifications. It's suggested that short and long GRBs likely originate from different physical processes. Short ones may be from merging neutron stars, long ones from the collapse of massive stars, so getting the classification right is important.
So how did AI approach this? Did it just use the duration or something else?
This is where it gets interesting. The researchers aimed for a more innovative approach. They wanted to classify GRBs using their spectral information instead of relying solely on the T90 duration parameter. The idea was to see if the light signature itself held clues to the burst type, independent of duration. They compiled a dataset of nearly 3,500 GRBs from the Fermi Gamma Ray Space Telescope's GBM catalogs. Each burst was characterized by over 300 parameters describing its spectral and temporal properties. A significant challenge they immediately faced, though, was data imbalance. Long-duration bursts vastly outnumbered short ones in their dataset by almost 6-to-1. This imbalance can skew how an AI learns.
Right, the AI might just learn to always guess long burst and still get a high accuracy just because they're more common.
Precisely. So first, they did a feature selection process. They used techniques like support vector machines on various spectral parameters, things like FLUX BAT64 and FLNC band ERG-FLUX, to identify which features were most relevant for distinguishing between the two types. Some combinations showed very high accuracy, over 95%, just based on these spectral features alone. Then, they fine-tuned the GPT 3.5 turbo model on about 75% of this data. Initially, it achieved an overall accuracy of just over 95%. But, as you suspected, due to that data imbalance, the accuracy for long bursts was extremely high, nearly 99.5%, while the accuracy for the rarer short bursts was considerably lower, around 74%.
Okay, so the imbalance was definitely an issue. How did they address it?
They equalized the training sample sizes. Essentially, they reduced the number of long-duration GRBs in the training set to match the number of short-duration ones. They then refine-tuned the model on this balanced dataset. After this adjustment, the overall accuracy shifted slightly to about 91%. But critically, the accuracy for short-duration bursts jumped significantly to over 92%, while long bursts were still classified correctly almost 90% of the time. The classifications became much more balanced and reliable for both types.
That's fascinating. So the key finding here is that the fine-tuned GPT model could indeed classify GRBs based purely on their spectral characteristics, supporting the idea that short and long bursts really do have distinct radiation properties beyond just how long they last.
Exactly. It's a significant scientific finding in itself, suggesting fundamental differences in the emission mechanisms, and the AI helped uncover, or at least strongly support this efficiently, by analyzing the spectral data.
Okay, one more major test before we move on. You mentioned estimating black hole spin and inclination. This sounds like one of the most fundamental and incredibly challenging tasks in astrophysics.
It really is up there. Measuring black hole spin is crucial. It serves as a vital test for Einstein's theory of general relativity in the most extreme gravitational fields imaginable, how space-time itself is twisted by a spinning massive object. And traditionally, this measurement is often performed by analyzing the subtle but characteristic broadening and distortion of the Fekal line that's an emission line of iron atoms. This line is produced by superhot matter swirling into the black hole in what's called an accretion disk. The shape of this line gets distorted by the black hole's gravity and spin.
So you look at the shape of this iron line and try to deduce how fast the black hole is spinning and how we're viewing the disk.
That's the idea. But it's incredibly complex modeling, so how did the AI tackle this? They used a simulation-based approach here. They couldn't just use observational data easily because getting clean enough spectra and knowing the spin inclination beforehand is basically impossible. So they generated thousands of simulated Fekal line profiles using relativistic models. First, they generated 1,000 profiles just by varying the dimensionless black hole spin parameter, which goes from 0 for no spin to 1 for maximum spin. Then they generated another 3,000 samples by varying both the spin value and the observation inclination angle of the accretion disk, basically, the angle from which we're viewing it. And again, to optimize processing for the GPT model, they streamlined these simulated spectra down to that 100 data point representation.
Okay, simulations make sense here. What were the results when GPT analyzed these simulated line shapes?
They were quite compelling, and they tested it in stages. Initially, when they fixed the spin direction relative to the disk and the inclination angle, varying only the spin value, the model achieved a median relative precision of nearly 97.5% in inferring that spin value. Pretty good.
Very good.
Then they made it harder. They varied the spin values and included both parallel and anti-parallel spin directions, meaning the disk rotates either with the black hole's spin or against it. Here, the fine-tuned model achieved perfect 100% accuracy in classifying the spin direction, parallel versus anti-parallel, and it still got over 98% median relative accuracy for the spin values themselves.
Wow, 100% on the direction. That's impressive.
It is, but they pushed it further. Finally, they simultaneously varied the spin direction, the spin values, and the inclination angles across 3,000 different simulated spectra. This is the most complex scenario, closest to a real observation where you don't know any of these parameters beforehand. Even here, the model maintained its perfect 100% accuracy in inferring the spin direction. For the numerical parameters, it achieved median relative accuracies of nearly 87% for the spin values and over 94.5% for the inclination angles.
Okay, so the accuracy for the spin value dropped a little bit in that most complex case, from 98% down to 87%.
It did, yes. The researchers attributed this slight decrease to the fact that they had to use a coarser sampling interval for the spin values when generating the simulations, simply to accommodate the much larger, more complex dataset covering all three varying parameters within computational limits.
Understood. But still, the overall takeaway seems really significant. This demonstrates a commendable capability for GPT to deduce these complex black hole parameters that are often incredibly difficult, sometimes impossible, to measure directly and accurately through traditional methods.
Absolutely. This wasn't just about classification like telling a star from a galaxy. It's about the AI extracting profound physical property spin, inclination directly from the spectral line shape data, even if it was simulated data in this case. It really reveals AI's potential to unlock parameters that are incredibly difficult to get at, pushing the boundaries of what we thought was possible in black hole research.
Okay, those are truly impressive practical achievements. It's clear AI can do an incredible amount. It classifies, it infers, it estimates with remarkable accuracy, processing these vast data sets with an efficiency we just can't match. But, as you said earlier, this inevitably raises that deeper, more philosophical question, the one that's right there in our Deep Dive's title. Can AI truly understand the universe? Or is it just, a hyper-efficient data processor, a statistical engine that's just incredibly good at pattern matching? The authors of that first paper, they clearly recognize this profound inquiry, didn't they? They delve into it much further in their follow-up work, reflections on, can AI understand our universe?
Exactly. This is where the conversation shifts, moving beyond just technical performance benchmarks and into the very nature of knowledge and understanding itself. The central philosophical question the authors pose isn't simply about whether AI can pass a specific test, like classifying galaxies. It's about whether it can, and I quote, deduce the generative principles of data through data analysis. That phrase, generative principles, is key. It implies moving beyond just recognizing patterns and statistical correlations towards something more akin to genuine scientific discovery, uncovering the underlying rules or laws that produce the data, perhaps even achieving theoretical insight. And the article highlights two core concepts that are central to human understanding: intuition and causality. And then it explores how AI might approach, or perhaps even surpass, these deeply human cognitive abilities.
Okay, let's start with intuition. How do they define human intuition in this context?
For humans, they describe intuition as our immediate understanding, often derived through sensory experiences. It's forming a clear image or getting an immediate comprehension without necessarily needing complex, step-by-step reasoning. Like when you see a tree, your vision instantly gives you its shape, its color, its approximate distance. You don't consciously calculate these things. It's an intuitive grasp based on sensory input processed by our brains. This is deeply tied to our brain structure and our specific sensory systems: sight, hearing, touch, etc. But, and this is a critical point they make, our senses are also incredibly limited. We only perceive a tiny sliver of the electromagnetic spectrum as visible light. We only hear a narrow range of sound frequencies. While instruments we build, like telescopes and microscopes, extend our perception dramatically, a lot of modern scientific understanding, especially in fields like quantum mechanics or cosmology, relies heavily on abstract data analysis and mathematical modeling that goes far beyond any direct human intuition based on senses.
Right. We can't intuitively feel quantum superposition or see dark matter. Our understanding there is built on math and indirect evidence.
Precisely. So if human intuition is fundamentally tied to and limited by our biological senses, what does it mean for AI to develop its own kind of intuition? Could it have a form of super intuition that transcends our limitations?
That's a fascinating idea. How could AI develop something like intuition if it doesn't have biological eyes or ears?
Well, the authors suggest AI's potential super intuition starts by simulating perceptions that are foundational to ours, but then goes much further. For instance, AI can certainly simulate 3D space perception using video and image data. Techniques like analyzing stereo images or processing LiDAR point clouds allow it to generate representations of depth and spatial layout. It understands time primarily through analyzing temporal sequences and rates of change in time series data, capturing dynamic variations and modeling how things evolve. But then AI extends far beyond this. Its perceptual capabilities, they argue, can be likened to having hundreds of eyes, and here eyes really means diverse sensory modalities or data input channels that are capable of simultaneously receiving and processing multidimensional data. Think about it in, say, genomics research. An AI can handle information across thousands of dimensions simultaneously, identifying complex correlations between genes, proteins, and disease states that a human simply cannot intuitively grasp or visualize. It forms a direct intuition about the structure within these high-dimensional data spaces.
So it's not limited to the 3 spatial dimensions plus time that we experience. It can sense patterns in hundreds or thousands of dimensions.
Exactly. And it also possesses, metaphorically speaking, eyes of different scales. It can process data from the molecular level all the way up to galactic scales simultaneously. Imagine an AI receiving data streams from electron microscopes, observing molecular interactions, while also processing data from large astronomical surveys mapping galaxy clusters. This unique ability allows it to potentially model and understand phenomena across these immense scales, achieving what they call cross-scale perception, looking for connections we might miss.
And it gets even stranger, doesn't it? They talk about nonlinear time perception.
Right. While our perception of time is largely linear, flowing forward, AI can perform nonlinear analysis of how data changes over time. It can look for complex temporal patterns, accelerations, decelerations, and it can even, in a sense, leap through time. For example, in analyzing a long video, an AI might skip frames strategically to identify overall trends or significant events without parsing every single moment sequentially. This nonlinear temporal analysis could potentially be applied to advanced prediction and retrospection in ways that are just not natural for us.
And then there's the idea of senses beyond our own 5.
This is perhaps the most profound aspect. AI can extend perception far beyond the human sensory range. It can effectively see the world through mediators like neutrinos. Neutrinos pass through almost everything, so detecting them allows AI to perceive physical phenomena occurring deep inside stars during supernova explosions, or even inside the Earth. It's like having X-ray vision for the most extreme events in the universe. And similarly, AI can utilize gravitational wave signals detected by instruments like LIGO and Virgo to effectively hear space-time vibrations. This allows it to perceive the motion, merger, and evolution of incredibly massive objects like black holes and neutron stars, events completely invisible to traditional telescopes. So this combination, multidimensional, multiscale, multimodal perception, including senses beyond ours, is what could allow AI to identify underlying commonalities and generate insights in completely novel ways. It might lead to a fundamentally deeper comprehension of events and phenomena than humans alone can ever achieve through our limited sensory apparatus.
Okay, that's a mind-bending perspective on AI intuition. What about the other core concept? Causality. How do humans understand cause and effect, and how might AI compare?
Right, causality. What does it mean for us to truly understand the causality of an event? The paper uses the simple example. The sky rains, so the ground gets wet. That's a basic causal relationship we observe. But why does it rain? And how mechanistically does rain cause the ground to become wet? For humans, our understanding of causality exists on multiple levels. It ranges from simple pattern matching, like a child learning, through repeated observation that rain leads to wet ground, all the way to deep theoretical explanations involving meteorology, physics, understanding condensation, gravity, surface tension, absorption, and so on. We also employ counterfactual reasoning. We ask, would the ground have stayed dry if it hadn't rained? This helps us isolate the causal factor. But crucially, our human understanding of causality is always limited. It's limited by our current scientific knowledge. We can only explain things based on the theories we have. And it's limited by our cognitive capacity to process overly complex causal chains. We often have to rely on simplified models or heuristics.
So, given our own limitations in perceiving and processing complex causal chains, how does AI's approach to causality compare? Is it just incredibly sophisticated pattern matching on a grand scale? Or could it be something more profound?
Well, the authors argue that AI shares many similarities with humans in its approach to discovering causal relationships, but it has the potential to surpass us significantly in capability. Like humans, AI can extract potential causal links from complex environments by training on large data sets and recognizing statistical patterns. For example, analyzing correlations between weather data variables like temperature, pressure, and humidity to predict rainfall. Both humans and AI identify these correlations from observation, forming a foundation. And both humans and AI form and test hypotheses. Humans often do this intuitively or through controlled experiments. AI can do this more systematically using causal inference algorithms and running massive simulations to test the effects of interventions or explore counterfactual scenarios. What if this gene wasn't mutated?
Okay, but where does AI potentially surpass us?
The key advantages lie in its ability to handle scale and complexity far beyond human limits. First, processing vast data. AI can identify complex, subtle causal relationships hidden within high-dimensional data sets where human intuition simply fails. Think again about genomics. An AI analyzing millions of genetic variables across thousands of individuals might uncover complex causal pathways between multiple gene interactions and a specific disease, a task that would be practically impossible for human researchers to do manually. Or in climate modeling, understanding the intricate feedback loops between dozens of variables. AI uses techniques like Bayesian networks or structural equation modeling to map out these hidden causal structures in noisy, complex data.
So it sees causal links in complexity that we just can't perceive?
Exactly. Second, AI excels at efficiently validating and testing causal hypotheses on a massive scale. It can simulate those counterfactual scenarios far more extensively and rapidly than we can. Imagine predicting the likely effects of thousands of potential gene edits on disease progression without conducting decades of laborious lab experiments, or simulating countless molecular interactions to understand how a potential drug might causally affect a biological pathway. AI can explore the causal landscape much more thoroughly. And third, AI can potentially handle much more complex, deeply nested causal chains. Think about understanding the cascading effects from molecular behaviors up to ecosystem-level dynamics, or unraveling the intricate mechanisms driving nonlinear systems in fields like ecology or economics. AI can build and analyze these deeply layered causal networks in a way that quickly overwhelms human cognitive capacity.
So the implication isn't just faster analysis, it's potentially a more comprehensive, deeper understanding of causality itself.
That's the profound implication the authors suggest. AI has the potential to offer unprecedented efficiency and comprehensiveness in understanding causality, going far beyond what our current cognitive limitations allow. It's not merely pattern matching, it's the ability to systematically explore, model, and verify causal links on scales and levels of complexity previously unimaginable.
That's a truly mind-bending thought. AI developing its own kind of super senses and potentially a deeper grasp of cause and effect than we have. But how is this even possible technologically?
Yeah.
What are the foundational engines driving these AI capabilities, allowing them to achieve these incredible feats and maybe develop this new kind of understanding? Let's unpack the tech behind it.
Okay. At the very heart of modern large language models like GPT, the foundational technology is the transformer architecture. And the absolute core feature of the transformer is the attention mechanism. This mechanism was revolutionary because it allows the model to dynamically weigh the importance of different parts of the input data when generating an output. Essentially, it lets the model focus on what's most relevant in the context, giving it a much better sense of, well, context and relevance than previous architectures.
It pays attention to the right words, so to speak.
Exactly. This is often broken down into two key types. Self-attention is where each word in a sentence, for example, attends to all other words in that same sentence to understand their relationships and how they modify each other's meaning. Then there's multi-head attention, which takes this a step further. It employs multiple parallel attention mechanisms simultaneously. Each head can learn to focus on different types of relationships or different semantic features. Maybe one head focuses on grammatical structure, another on semantic similarity, another on positional information. This allows the model to capture a much richer and more diverse understanding of the input.
And the paper draws some interesting analogies to physics here.
Yes, they do. They suggest that just as physical equations describe interactions between particles and define the strength of those interactions through precise parameters, the attention weight matrices within the transformer numerically encode relationships and directionalities between words or data points. The model then iteratively generates its output, like text, essentially finding a solution that satisfies the constraints imposed by the input data and these learned attention weights. It's somewhat analogous to how a physical system evolves over time under the influence of forces and initial conditions. They even draw a parallel, perhaps more metaphorically, to quantum mechanics. Multi-head attention allows each word or token to effectively exist in multiple states or views simultaneously based on different attention heads until these views are consolidated into a final representation. This mirrors, in a loose sense, the quantum principle of superposition.
So the architecture itself isn't necessarily thinking or reasoning in a human way.
Correct. The authors are clear that the transformer architecture itself doesn't inherently perform human-like reasoning. However, they point out that the nonlinear combination of many of these transformer units stacked in layers within these massive, large-scale networks can lead to emergent properties. These emergent behaviors can resemble logic, reasoning, and even understanding causality, much like complex cognitive functions emerge from the interactions of simpler neurons in biological brains.
Okay, so the transformer and attention are the foundation. But then there's this other key innovation you mentioned, chain of thought reasoning, or COT. What's that about?
Right. COTI is a technique that significantly enhances the logical reasoning capabilities of LLMs. The key idea is that instead of just outputting a final answer to a complex question or problem, the AI is prompted or trained to explicitly generate the intermediate steps, the chain of thought, that lead to that answer. It simulates a human-like process of breaking down a problem and working through it step by step.
So the AI is literally showing its work, not just jumping to a conclusion. How much does that help with trustworthiness, especially in scientific applications where you need to know how an answer was reached?
It helps enormously. That's a crucial point. It significantly enhances transparency and trustworthiness. These intermediate steps aren't just random text. They are often captured by what researchers call reasoning tokens. These are special internal representations within the model that encode the logical transitions between steps, allowing the model to dynamically utilize prior reasoning information as it proceeds. Mathematically, you can think of COT reasoning as decomposing a complex problem into a series of simpler, logically related subtasks. This makes the entire reasoning process much more transparent and, importantly, more controllable and verifiable.
And how is it trained to do this?
The training process for CUT often combines both supervised learning, where it's shown examples of correct reasoning steps, and reinforcement learning, where it's rewarded not just for getting the final answer right, but also for the logical soundness and coherence of the intermediate steps. And modern LLMs often support incredibly long context windows, now some models up to 128,000 tokens. This allows them to handle highly complex tasks requiring long chains of reasoning, like multi-step mathematical proofs or complex scientific arguments. They use dynamic management techniques to focus on the relevant parts of this vast context and avoid getting lost or overloaded.
That transparency seems vital. If you're using AI in theoretical physics or maybe medical diagnostics, you absolutely need to understand how it arrived at its conclusion, right?
Absolutely. It moves AI away from being a mysterious black box towards being a more understandable and verifiable collaborator in the scientific process.
Okay. And then there's the third major technological enabler, multimodal processing. This is about handling more than just text.
Exactly. This marks a significant evolution for LLMs, their growing ability to handle and, crucially, integrate various types of data beyond just text. We're talking about images, speech, video, potentially sensor data, tabular data, you name it. The process generally involves several key steps. First is modal representation. Each different type of data, text, image, audio, etc. needs to be converted into a format the AI can understand, typically high-dimensional vector spaces or embeddings. This is done using specialized feature extractors like sophisticated computer vision models for images or speech recognition models for audio. Think of it as creating a common mathematical language for different senses. Second is modal alignment. Once you have these vector representations for each modality, you need to map them into a shared semantic space. This is where the different types of information can be directly compared, contrasted, and understood in relation to each other. You need to align the concept of apple in text with the image of an apple. And third is information fusion. This is where the magic happens. The AI combines the information from these different aligned modalities. This often uses cross-attention mechanisms within the transformer architecture, allowing information from one modality to influence how the AI processes another. For example, a text query like, "Show me the quasar in this image," can guide the AI's visual attention to the relevant region of an astronomical image.
And why is this multimodal capability so powerful specifically for understanding the universe?
Oh, it's immense. It enables AI to perceive and understand complex scientific phenomena from multiple perspectives simultaneously. Imagine an AI integrating optical telescope images of a galaxy with its radio wave emissions, its X-ray signature, data from simulations about its formation, and textual descriptions from scientific papers analyzing it. That provides a much richer, more holistic understanding than any single data type alone. It also, crucially, allows AI to process data that lies entirely beyond human sensory perception. As we discussed, much of the universe reveals itself in wavelengths we can't see, infrared, ultraviolet, X-rays, gamma rays, or through channels like gravitational waves or neutrino signals. Multimodal AI can potentially integrate all these diverse signals into a coherent picture.
Right, it's not limited by our biology.
Exactly. And furthermore, it allows AI to handle data across vastly different spatial and temporal scales more effectively. It could analyze microscopic molecular structures from lab experiments alongside macroscopic cosmic formations from telescope data, or study millisecond-long reactions in particle accelerators alongside million-year evolutionary processes in galaxy simulations. This ability to bridge scales and modalities is key to potentially uncovering deep, cross-cutting patterns and causal relationships that would be completely invisible to us otherwise.
Wow, okay, so these technologies, transformers, chain of thought, multimodal processing, they need data, lots of it. And this brings us back to the ultimate source of information. We always talk about big data, but the paper makes a striking point.
Yeah.
What's the biggest data of all?
The answer, as they compellingly argue, is the data contained within our observable universe itself.
How do they frame that comparison?
They contrast the limits of knowledge obtainable just from Earth-bound experiments and observations with the vast informational horizon opened up by looking outwards. Our direct experience and experiments on Earth are confined to, relatively speaking, a minuscule radius they calculated as about 6.73 by 10 light years, basically the scale of our solar system explorations. But when we extend our observations beyond Earth, looking out into the deep sky with powerful telescopes, our informational horizon expands dramatically to the edge of the observable universe, which is approximately 46 billion light years in radius in every direction. This staggering expansion, they estimate, exponentially multiplies the information potentially available to us by something like 40 orders of magnitude. It doesn't just bring into view more stars and galaxies, it reveals the life of stars, life of galaxies, and a diverse array of cosmic phenomena, each operating under physical laws and conditions, offering unique insights into the universe's fundamental workings.
So it's not just more data, it's fundamentally different data that overcomes limitations we face here on Earth.
Precisely. They detail several fundamental limitations of being stuck on Earth that looking outward helps us overcome. First, cosmic composition. Earth, and indeed our entire solar system, is made almost entirely of ordinary baryonic matter, the stuff of atoms. But we now know this visible matter constitutes a mere 4.9% of the universe's total mass energy budget. The vast bulk, around 95%, is made up of mysterious dark matter and dark energy, entities whose nature and properties can really only be studied effectively on cosmological scales by observing their gravitational effects on galaxies and the universe's expansion. Second, extreme conditions. Earth exists under exceptionally mild and stable conditions compared to the rest of the cosmos. Most of the visible universe isn't solid, liquid, or gas, as we commonly experience it. It's in a plasma state, superheated ionized gas. The physics governing plasmas, especially under extreme temperatures and densities found in stars, accretion disks, or the early universe, is fundamentally different from everyday Earth physics. We need to look outward to study these dominant states of matter.
Our atmosphere also gets in the way, doesn't it?
Absolutely. Third, the atmospheric filter. While vital for life, Earth's atmosphere is opaque to most forms of electromagnetic radiation coming from space. It blocks almost all gamma rays, X-rays, and large portions of the ultraviolet and infrared spectrum. While space telescopes orbiting above the atmosphere have been revolutionary, they still only reveal parts of the full cosmic spectrum. We need diverse instruments in space, and sometimes even fundamentally different messengers like neutrinos or gravitational waves to get the full picture. Fourth, there are finite size constraints here on Earth. The physical size of our planet inherently limits the scale and power of experimental setups we can build. There's a maximum energy achievable in particle accelerators like the LHC, a maximum baseline length for interferometer arms used in gravitational wave detection like LIGO Virgo, and a maximum resolution achievable by linking radio telescopes across the globe in networks like the Event Horizon Telescope. To probe certain scales or energies, we might ultimately need space-based instruments or rely on cosmic phenomena themselves as natural laboratories. And finally, there's a practical point about data accessibility. Unlike sensitive geographical, commercial, or societal data, which often contains proprietary information or personal privacy concerns, astronomical data is frequently non-proprietary. It's often considered of universal interest. It's typically released openly to the global scientific community by space agencies and large observatories, and benefits from well-established technical standards for data formats and accessibility, like the Virtual Observatory Framework and the FITS data format. This makes astronomical data uniquely suitable and accessible for large-scale AI training and analysis.
Okay, so AI needs vast, diverse data. The universe provides that data, overcoming Earth's limitations. This confluence seems to lead us directly to an inevitable conclusion, doesn't it? We are truly entering, or perhaps are already well within, the era of massive global scientific instruments designed to capture this cosmic data.
Indeed. There's a profound symbiotic relationship emerging, as the authors highlight. AI, particularly these large foundation models, needs these expansive, high-quality data sets to learn, grow, and reveal complex patterns. And these large scientific facilities, next-generation telescopes, detectors, colliders, are precisely what generate these immense volumes of data, often at unprecedented rates. Conversely, the sheer volume and complexity of the data pouring in from these facilities, terabytes or even petabytes per day, in some cases absolutely necessitates the creation and advancement of sophisticated AI and machine learning techniques. Humans simply cannot process or analyze this data deluge effectively or efficiently without AI's help. It would take lifetimes. This synergy is why, when you examine the major astronomy and physics white papers and strategic roadmaps published over the last few years, looking ahead 10, 20 years from major scientific players like the United States, Europe, China, you find this unanimous and incredibly strong focus. They are all planning massive investments in the construction and operation of new, large-scale scientific facilities.
Can you give us some specific examples of these upcoming mega projects?
Absolutely. Let's look at NASA and its international partners, drawing from their decadal surveys. Over the next decade or two, they're planning dozens of ambitious missions under broad themes like worlds and suns in context, new messengers and new physics, and cosmic ecosystems. Key flagships include the Nancy Grace Roman Space Telescope, previously known as WO-FIRST. It's designed to tackle major questions about dark energy and exoplanets using wide-field imaging in the infrared. It will survey huge areas of the sky, generating enormous data sets. Then there's the Laser Interferometer Space Antenna, or LISA. This is a multi-billion-dollar planned space mission involving 3 spacecraft flying in formation millions kilometers apart to detect low-frequency gravitational waves ripples in space-time itself. LISA promises unprecedented insights into merging supermassive black holes at the centers of galaxies, the history of the universe's expansion, and potentially new physics. And missions like the Dragonfly rotorcraft plan to explore the surface of Titan, Saturn's largest moon, searching for prebiotic chemistry and signs of potential habitability. Each of these generates unique, complex data requiring advanced analysis.
And Europe has similar ambitions.
Very much so. The European strategy, outlined in documents like the Astronet Science Vision and Roadmap, explicitly calls the period from 2022 to 2035 an era of big science, big data. They are planning not just upgrades to existing facilities, but also major new ground-based and space-based detectors. On the ground, the flagship is the Extremely Large Telescope, or ELT, being built in Chile. With its nearly 40-meter primary mirror, it's designed to study everything from the first galaxies to the atmospheres of exoplanets in unprecedented detail, potentially even directly imaging Earth-like planets around nearby stars. In radio astronomy, there's the Square Kilometer Array, or SKA. This isn't just one big telescope, it's a vast network of antennas spread across South Africa and Australia, eventually forming a collecting area of 1 square kilometer. SKA is designed to fundamentally rewrite our understanding of cosmic magnetism, how the first stars and galaxies formed during the cosmic dawn, test gravity in extreme environments, and even hunt for signs of extraterrestrial intelligence by surveying billions of star systems. In space, Europe has missions like the Euclid Space Telescope, recently launched, designed to map the geometry of the dark universe by precisely measuring the shapes and redshifts of billions of galaxies to understand dark energy and dark matter. There's also the Plato Space Telescope, planned for launch soon, which will focus specifically on discovering and characterizing Earth-like planets orbiting Sun-like stars in their habitable zones. And other missions, like JUICE heading to Jupiter's icy moons, Ariel focusing on exoplanet atmospheres, the Comet Interceptor mission, Envision heading to Venus, plus continued involvement in Mars exploration with rovers like Curiosity and Perseverance. Critically, the European roadmap explicitly emphasizes significant investment in the computing infrastructure and data management needed to handle the data tsunami from these facilities, promoting a collaborative and open data ecosystem across astrophysics.
And China is also a major player in this arena.
Absolutely. China's Astronomy Development Strategy 2035 outlines similarly ambitious initiatives, prioritizing major investment in large scientific facilities across the electromagnetic spectrum and beyond. Their upcoming projects include the Chinese Space Station Telescope, or CSST, also known as Zhentian. This will be a large optical UV telescope co-orbiting with their space station, conducting wide-field surveys comparable in scope to Euclid or Roman. On the ground, they plan the FAST Array, or FASTA, which will expand their existing 500-meter aperture spherical radio telescope, FAST, already the world's largest single-dish radio telescope, into an even more powerful array. They're also planning advanced optical and infrared telescopes, including facilities at the High Altitude Antarctic Kunlun Station for unique observing conditions, like the Large Optical Infrared Telescope, LOT, and the 6.5-meter multiplexed survey telescope, MUST-T. They're also planning deep space probes, like the Tianwen-4 mission targeting Jupiter in its system, and dedicated space telescopes for specific science goals, like the Hot Universe Baryon Surveyor, HUBS, to study the diffuse hot gas in galaxy halos, and the proposed Census of Warm-Hot Intergalactic Medium Accretion Feedback Explorer CAE satellite focusing on ultraviolet emissions, plus massive new ground-based radio telescopes like the Xinjiang Kitai 110-meter telescope, QTT.
It's truly a global endeavor, this push for bigger instruments.
It is, and the paper makes an interesting economic point, too. While advancements in AI and machine learning are dramatically reducing the cost of inference, the cost of analyzing data once you have it, the cost of acquiring specialized, unique, high-quality data is actually rising, precisely because it requires these massive, expensive new facilities. This economic principle, they argue, ensures continued human investment in obtaining this unique data. It makes this era of large scientific equipment not just a scientific ambition driven by curiosity, but also something of an economic inevitability if we want to keep pushing the frontiers of knowledge. AI needs the data, and getting that data requires these huge investments.
Okay, so we have these incredible AI tools being developed, fueled by data from ever larger cosmic observatories. The potential seems immense, but it can't all be smooth sailing, right? Despite all these advances, AI's journey towards truly understanding the cosmos surely isn't without its hurdles, its limitations, its challenges. It's not a magic bullet, at least not yet.
That's a crucial point to emphasize. No, it's definitely not a magic bullet, and the researchers are very aware of the current challenges and limitations. One of the significant concerns they raise relates to what's often termed alignment in the broader field of AI development. There's an inherent tension potentially between the goal of aligning AI systems with human values and ensuring safety, and the specific needs of scientific exploration, which often requires pushing boundaries, encountering the unexpected, and dealing with anomalous data that might not fit neatly into predefined categories. They even encountered a practical technical challenge related to this during their own fine-tuning experiments. They found that including certain types of real spectral data in their training samples could actually prevent the fine-tuning process from proceeding successfully. The reason wasn't entirely clear, but they speculate it might be due to automated safety systems within the large language model, designed for general purpose use, flagging some scientifically valid but perhaps unusual-looking spectra as potentially problematic or harmful content according to its general rules.
Wow, so a safety filter designed for, say, filtering text could inadvertently block potentially crucial scientific data.
Exactly. This becomes a significant issue because genuine scientific discovery often relies precisely on encountering and understanding previously unseen or anomalous phenomena, things that don't fit the patterns the AI has already learned, or that might look strange compared to typical data. If safety guardrails are too broad or inflexible, they could inadvertently hinder the very scientific exploration AI is supposed to enable. It highlights a real tension between ensuring robust, general-purpose safety and allowing for the sometimes messy, unpredictable nature of cutting-edge scientific research.
That's a really interesting and subtle challenge. What other limitations do they discuss?
Another concern they touch upon revolves around the concept of randomness. Current large language models, despite their sophistication, don't exhibit true randomness in the way many natural processes seem to, like quantum fluctuations or radioactive decay. Their randomness, when they generate varied outputs, for instance, is typically pseudo-random. It's generated by deterministic algorithms, meaning if you knew the exact algorithm and the starting seed value, you could, in principle, predict the output perfectly. It just looks random to us. While AI training certainly uses probability theory extensively to model distributions and uncertainties in large data sets, the authors raise the question: can an AI built on deterministic or pseudo-random foundations truly understand or incorporate the inherent fundamental randomness that seems to be a key aspect of our universe's richness and complexity? From the probabilistic nature of quantum events to the chaotic dynamics in stellar evolution or galaxy interactions, true randomness plays a crucial role. It's uncertain if current AI architectures can fully grasp or model this intrinsic stochasticity.
And then there's the issue of language itself.
Yes. The third major concern they raise is language. LLMs are fundamentally based on human language. They learn from text, they process information often represented linguistically, and they output language. But, the authors argue, human language is demonstrably not a complete set for describing everything in the universe. Some phenomena, especially newly discovered ones at the frontiers of science, or concepts in highly abstract fields like advanced mathematics or theoretical physics, may simply not be adequately understandable or representable through natural language alone. There might be aspects of reality for which we simply lack the words or grammatical structures. They draw an analogy here to quantum mechanics again. Just as in quantum mechanics, a chosen set of basis states might not be sufficient to fully represent all possible observed states of a system, human language might lack certain fundamental basis concepts or descriptive frameworks needed to fully capture the intricacies of certain physical realities. Some meaning, some nuance, some essential structure could potentially be lost in the translation from raw observational data or complex mathematical formalism into the human linguistic concepts that an LLM primarily operates on.
Can you elaborate on that contrast between natural language and, say, mathematical language in science?
Sure, think about their core characteristics. Natural language, English, Chinese, Spanish, etc., is incredibly rich, flexible, and powerful for communication, storytelling, expressing emotion. But it's also inherently complex, often deeply ambiguous, constantly evolving, highly context dependent, and exists in thousands of mutually unintelligible variations across the globe. Mathematical language, on the other hand, strives for precision, logical consistency, and universality. Its symbols and rules are strictly defined. It evolves through rigorous proofs and logical deduction. While it might seem colder or more constrained, it's the bedrock of natural science, precisely because it provides a concise, unambiguous, and universally understandable way to express quantitative relationships and logical structures. The challenge arises, as the authors note, when trying to do science or do math entirely within the framework of natural language, as an LLM primarily does. You inevitably face substantial difficulties due to that inherent ambiguity, the potential incompleteness of language for certain concepts, and a pervasive loss of precision compared to formal mathematical or logical systems. While selectively translating between mathematical results and natural language explanations can be incredibly useful for building intuition and communicating findings, relying solely on natural language processing for rigorous scientific reasoning and discovery poses fundamental limitations for certain types of deep scientific insight that rely on mathematical rigor.
That leads perfectly into the next point, which seems almost ironic, doesn't it? These incredibly sophisticated language models, capable of digesting galaxies worth of text and data, generating complex narratives, can still struggle with something as seemingly fundamental as precise mathematical calculation. Given that limitation, does it fundamentally constrain AI's ability to develop a true scientific understanding, which so often relies on math, or is it just a technical hurdle to overcome?
It is indeed a striking and somewhat ironic limitation that persists even in the most advanced models. The researchers actually present self-assessments from various popular AIs themselves, GPT 3.5, GPT 4, Bing Chat based on GPT, Claude, and even an open source model called Alpaca Lara, asking them about their own mathematical capabilities. And the consensus generally is an admission of their shortcomings. They can typically handle basic arithmetic, maybe solve simple word problems or algebraic equations expressed in text, but their performance decreases significantly, often dramatically, as the mathematical complexity increases. They are fundamentally not optimized for complex symbolic manipulation, high-precision numerical computation, or abstract mathematical reasoning in the way that specialized computer algebra systems or numerical libraries are. As the AI Claude eloquently puts it in its self-assessment, they often lack deeper meaning or reasoning in mathematics. They might generate answers that look plausible, sometimes even expressing them with high confidence, but which are actually logically flawed, based on spurious patterns or simply incorrect. Their mathematical skills are primarily based on recognizing patterns in how mathematical language is used in their training data, rather than on a true underlying mathematical insight or deductive capability.
So, how can this be improved? What are the proposed solutions?
Researchers and the AIs themselves suggest several potential avenues to improve mathematical abilities. Obvious ones include training them on much larger and more diverse data sets of mathematical problems and their step-by-step solutions. Another key approach is integrating specialized external tools, essentially allowing the LLM to call upon dedicated math libraries like SIMPy for symbolic math, or NumPy for numerical calculations when needed, rather than trying to do the math itself using language patterns. Architectural changes are also proposed, perhaps introducing specialized neurons or modules within the AI architecture specifically designed for arithmetic or logical operations. Fine-tuning models specifically on mathematical reasoning tasks is another strategy. Developing hybrid models that explicitly combine the language strengths of LLMs with the computational power of traditional calculators or symbolic engines is also being explored. Other ideas include enabling more interactive learning, where the AI can ask clarifying questions or learn from human feedback on its mathematical reasoning, and using curriculum learning, where the AI is trained on progressively harder mathematical problems, starting from the basics. Claude, in its self-assessment, adds some particularly interesting suggestions. Developing an internal mathematical knowledge graph to give the AI a more structured, conceptual understanding of mathematical objects and relationships beyond just word co-occurrence. Applying heuristic biases during training that explicitly encourage mathematically valid reasoning steps. Allowing interaction with human mathematicians during training or fine-tuning to learn logical deduction. And crucially, requiring the AI to rigorously explain its mathematical reasoning steps, forcing it towards a more structured and verifiable process.
But the core takeaway remains.
The core takeaway, however, seems to be that while simply scaling up current LLM architectures with more data and compute can lead to some improvement in quantitative reasoning abilities, their fundamental design as language pattern matchers likely imposes inherent limits on achieving true, deep mathematical understanding. Real mathematical insight seems to require something more than just pattern recognition, perhaps abstract reasoning, symbolic manipulation capabilities, and a grasp of logical necessity that isn't native to these architectures yet. Bridging that gap between linguistic pattern matching and genuine mathematical understanding remains a major active area of research.
Okay, so faced with these immense potentials, but also these significant challenges, alignment, randomness, language limitations, mathematical reasoning, where do the researchers suggest we go from here? How should we guide AI development if the goal is to genuinely help us understand the universe?
In light of both the potential and the pitfalls, the researchers propose a really profound guiding principle for future AI development in science. They call it, look outward and explore inward. The look outward part refers to what we discussed earlier, leveraging the vast data streams from the universe itself, gathered by our large scientific facilities. But the explore inward part is about the goal of that exploration. They argue that when humans ask why, when we seek understanding, we instinctively search for simple underlying building blocks, fundamental principles, physical laws that can explain the complex phenomena we observe. Think of how Newtonian gravity explains planetary orbits, or how quantum mechanics explains atomic spectra. The world appears incredibly complex, from subatomic particles interacting up to the cosmic web of galaxies. But the hope, the driving force behind much of fundamental physics, is that the ultimate theory of everything, if it exists, should be fundamentally simple, elegant, and comprehensible. AI, with its unparalleled capacity to analyze vast datasets and identify subtle patterns far exceeding human abilities, is uniquely positioned, they suggest, to help us in this inward exploration. It might be able to identify these simpler, fundamental patterns hidden within the complexity, potentially uncovering new building blocks for our understanding of the universe that we might otherwise miss.
So the idea isn't necessarily that AI needs to understand the final theory of everything itself.
Exactly. Their perspective is subtly different. The role of AI isn't necessarily to understand the ultimate theory once it's found, because if that theory is truly fundamental and simple, it should ideally be comprehensible to human minds as well. Instead, AI's crucial role could be to help us find that ultimate theory in the first place by sifting through the overwhelming complexity of data and revealing the underlying simplicity. Once that simpler theory is discovered, perhaps with AI's assistance, then both humans and AI could potentially comprehend it.
That's a fascinating way to frame AI's contribution. And do they propose any specific architectural ideas for building AI that could help achieve this inward exploration?
Yes, they propose a novel architectural concept they term AI's series expansion and hierarchical alignment. It's a way of thinking about structuring these incredibly complex AI models. They view a highly capable AI, metaphorically, as an exceedingly complex mathematical function. Just like many complex functions in physics or mathematics can be represented as a series expansion, like a Taylor series, a sum of simpler terms, they propose that a sophisticated AI could be conceptually expanded into numerous interconnected sub-AIs, ranging from very simple to very complex. The lower-order sub-AIs in this hierarchy, perhaps corresponding to simpler terms in the expansion and having fewer neurons or parameters, would ideally be simple enough to be manageable, understandable, and verifiable by humans. The higher-order sub-AIs, representing more complex terms, could be responsible for the model's more advanced, potentially superhuman capabilities, building upon the foundation laid by the simpler ones. The really intriguing idea is what they call the zero-order sub-AI. This represents the most fundamental, simplest component in the expansion. They speculate that after extensive training aimed at uncovering fundamental principles, this zero-order sub-AI might converge towards being composed of very simple mathematical structures, perhaps simple matrices. These simple structures could represent the fundamental building blocks or laws the AI has discovered, which are then elaborated upon and combined by the higher-order sub-AIs to model the complex reality we observe. It's like finding the simplest set of rules from which complexity emerges.
And what would be the benefits of structuring AI in this hierarchical way?
They suggest several potential benefits, particularly related to safety, explainability, and evaluation key challenges in AI development. Firstly, for safety and control. Humans would aim to retain understanding and control primarily over the foundational, simple, zero-order sub-AI. The idea is that without this fundamental base being correct and aligned, the entire complex system built upon it might fail to function properly or produce reliable results. control the foundation, control the system. Secondly, for explainability. Our primary goal in fundamental science is often to grasp the most fundamental principles, not necessarily every intricate detail of the complex emergent phenomena. So, the focus for human understanding and explanation wouldn't need to be on deciphering the incredibly complex workings of the highest order sub-AIs. Instead, we would focus on understanding the structurally simpler, lower order AIs, especially the zero order one, because that's where the fundamental insights are expected to reside. Ideally, the training process itself would be designed to simplify these lower order matrices over time, making the core principles the AI discovers progressively clearer. Thirdly, this structure could aid in evaluation. A major looming challenge is how to evaluate the accuracy or trustworthiness of an AI whose capabilities significantly surpass human understanding in a domain. How do you know if a superintelligent AI's answer about theoretical physics is correct? This hierarchical structure offers a potential pathway. Instead of just evaluating the final complex output, we could also evaluate the training process by monitoring the complexity and changes within the components, the matrices of the low-order sub-AIs. Proper training aimed at uncovering fundamental laws should, they hypothesize, lead to a simplification and stabilization of these lower-order matrices, ultimately affecting the zero-order sub-AI and ensuring its convergence towards something consistent with basic known physical laws, even as the higher-order components become incredibly complex. It provides an internal check on the AI's grasp for fundamentals.
So, this hierarchical approach offers a potential framework for building AI that is not only powerful, but also potentially safer, more interpretable at its core, and evaluable even when it operates beyond direct human comprehension.
That's the hope and the direction they propose exploring. It's a conceptual framework for aiming AI not just at solving problems, but at uncovering the fundamental simplicity underlying the universe's complexity.
This entire journey, from fine-tuning GPT on Starlight to contemplating hierarchical AI architecture searching for fundamental laws, it really feels like we're on the cusp of something profound. The fine-tuning of these models with astrophysical data has undeniably opened a truly revolutionary window into AI's potential, not just to process cosmic data, but perhaps even to interpret and, in some meaningful way, begin to understand the universe's incredible complexities. As we stand at the precipice of this new era, it seems unequivocally clear that integrating AI deeply into scientific research won't just augment our existing capabilities exponentially. It seems poised to fundamentally redefine the very boundaries of what's possible in cosmic discovery, maybe even in our quest for fundamental understanding itself. And this deep dive, it leaves us with a truly provocative final thought, something for you to really mull over long after we finish here. Let's cast our minds back, way back to 1961. There was a famous gathering of legendary physicists at MIT debating the future of physics. Channing Yang, a Nobel laureate known for his deep insights but also his caution, expressed a somewhat pessimistic view. He believed that achieving deeper levels of understanding in physics would become progressively, perhaps exponentially, more difficult, a never-ending, ever-steeper climb. Richard Feynman, another giant of 20th century physics, known for his brilliant intuition and boundless optimism, offered a starkly contrasting vision. He famously suggested that a final solution, a complete understanding of the fundamental laws of physics, might actually be imminent, perhaps achievable within a mere 100 years from that time. Now fast forward more than 50 years later to 2015. Channing Yang revisited this very question. He reflected on the decades of immense effort by the global physics community since 1961. And he noted, somewhat soberly, that all that effort had arguably yielded only one definitively deeper level of fundamental understanding, largely encapsulated by the standard model of particle physics. He then speculated that reaching the next truly fundamental level, going beyond the standard model, could take even longer than the previous 50 years, maybe much longer. So here's the question for you listening now. With the advent of artificial intelligence, this powerful new tool, this infant in its cradle today, as the researchers poetically describe it, which of these profound visions, Yang's cautious ascent or Feynman's optimistic final solution, will prove closer to the truth? In another 50 years, say, looking back from the year 2075, will we find ourselves still grappling with the same fundamental questions, having made only incremental progress, as Yang feared? Or will AI have helped us penetrate to just one more deeper level of understanding, confirming Yang's revised timeline? Or perhaps, is it possible that AI will act as an unprecedented accelerator, propelling our understanding forward at a rate previously unimaginable, actually helping us reach something akin to Feynman's envisioned final solution to the universe's most profound mysteries within the coming decades? The journey ahead is undeniably as vast and unexplored as the universe itself. But now, perhaps for the first time, we venture forth with a potential new kind of guide, an artificial intelligence, holding the promise, or at least the expectation, of revealing marvels previously undreamt of. What stands out most to you from today's deep dive into AI and the cosmos?